All right, let's get some more practice with partial derivatives. Find both partial derivatives for the following functions. So first, x derivative. Again, treat y as a constant. The x is the only variable. The y squared could be a constant out front, multiplying the entire thing. The derivative of this would be 0 plus 3x squared, and it couldn't hurt to simplify that. 3x squared times y squared. The y derivative, almost essentially the opposite. We treat x as constant. Then the 1 plus x cubed remains constant, and we simply take the derivative of the y squared, which would be 2y. And that's really it. Moving on. Our function is e to the x times sine of y. Let's use the alternative notation here. F sub x, or the x derivative, treat y as a constant. That means sine of y is all constant. So we'd have the derivative of e to the x times sine of y. And we just noticed that we did get this by taking the derivative of e to the x, which just is e to the x again. The y derivative will look a little more interesting because this time the e to the x is the constant part. X is treated as a constant when we're taking the y derivative, and then we have sine of y. The derivative of sine of y is going to be cos of y. Notice there's no product rule being used here because we always have a constant times our variable, or a function of our variable, or a constant times the function of this variable. So we don't need the product rule here for these particular instances. What about something like this? Let's take the y derivative of f. Oh, let's stick with our old order, x first, then y. So sometimes we can write it as a verb. Take the x derivative of f. Then the 1 over 4y, again, it's just a constant. Take it out front. And then the derivative of the x squared is 2x. Df dy of our function. This is where it gets a little more complicated. We have x squared over 4. That part would all be our constant. And then we have y to the negative 1. The derivative of y to the negative 1 with respect to y is negative y to the negative 2. Multiply by the exponent and then subtract 1 from the exponent. Alright, here's a more exotic beast down here. Take a look and we'll review it in a second. Alright, so remember, if we're taking the y derivative, this is constant, and this is constant. And so keep this in mind. The y derivative of x by itself, what's the derivative of any constant? 0. When y changes, x doesn't change, so the rate of change here has to be 0. This, when we take the derivative with respect to y, is going to become 2y, so we can scan down here. We're pretty much looking at this one here. The derivative of 10, of course, is sec squared. So yes, we're actually looking at B as our answer here. And that's it. Just practice, practice, practice until those concepts and those skills feel fluid to you. All right, more exotic, and we're going to add some points to the functions that we're looking at. So here, the x derivative as a formula would be 2x sine of y. This is constant. Derivative of x squared is 2x. The derivative of e to the anything is e to the same thing again times the derivative with respect to x this time of the exponent, which would just be y squared. We might as well get the formula for the y derivative while we're here. This time we differentiate the y part, keep the x squared as a constant. And again, the derivative of e to the anything is e to the same thing again, followed up with the derivative with respect to y this time of the exponent, and that'll give us an x times 2y. There we go. Now we can focus our attention at a particular point if we so choose. So this is the general form or the general formula for the x slopes and y slopes down here anywhere on the surface. Anywhere on the surface that's defined by z equals f of xy. Now we're getting the slope values at a particular point. So we just plug in the values 1 and 0. At 1 and 0, to make this clear, f sub x, the x derivative, and we'd often write it this way as at 1, 0, is going to be 2 times x is 1. Let's get this corrected here. X is 1, sine of y is 0, plus e to the 1 times 0 squared. And that, if we're careful, turns out to be a big whopping 0. Meanwhile, hopefully, we'll get something more interesting out of our y derivative. Our y derivative is x squared, so 1 squared cos of 0 plus e to the 1 times 0 squared times 1 times 2 times 0. Now this one is a little more interesting, fortunately. Cos of 0 is 1, so overall we get a slope in the y direction of 1 and a slope of x in the x direction of 0 at the particular point. So this is slopes, x and y slopes at a single point. Just comparing and contrasting the idea of a formula versus the idea of the values at a particular location. What does this tell us about the graph? Well, it can be a little challenging to interpret it at first, again, because we're dealing with 3D objects. We were at the point x equals 1, so x is this direction, y is that direction, that's z. I don't think we figured out the actual height there, did we? We could, though. F of 1, 0, just for the sake of curiosity, is 1 times 0 plus e to the 0, which is 1. So that's our z value, if we were to be graphing this. So our z value would be 1. Sneak up on this. There we go. That would be our point. And we found that the x slope at that point is 0, or flat, horizontal. So in that particular direction, nothing much is happening. The function is unchanging at that instant if we go front to back. Contrast that with left to right, and here it's going to be a bit of a challenge because the slope is 1. Let's draw this in down here. So that slope corresponds to a step in the x direction. Meanwhile, if we take a step in the y direction, I will underplay this a little bit for effect. But the y slope is 1. For every step we take in the y direction, we go up 1 in the z direction. So we have some extra interpretation about the shape of this function, even though the function itself is quite complicated. Off the top of my head, I have no idea what this graph would look like, but we do have some factual information about its shape around the point 1, 0 now that we can maybe use to get some insight into the overall shape, or certainly into what the function would be doing around this region of the surface.